Alrighty. Well, good morning, everybody. Thank you for joining us today at this early hour, as usual. We are meeting to talk about infrared spectroscopy, more specifically, the introduction to infrared spectroscopy. Last week, I gave you guys a small preview where I told you that molecules are not standing still. They're actually moving in many ways. They're rotating, they're translating, and they're vibrating. Specifically, the bonds of the molecules are vibrating, and you have your little water yoga dance, you know? Next big thing, I promise you. So we're going to actually talk about the details. What exactly is all this? What does it mean? How are we using it to see the squiggly lines? And how can we use the spectrum, the spectra, to figure out what it is that we have? So your first pre-lab quiz question was, what does IR stand for? It is infrared radiation, IR. Some people say that the I is inf and the R is rared, but that's not true. It's infrared radiation, IR radiation. IR spectroscopy is infrared radiation spectroscopy. So that would be the first question there. So what do we mean by that? Well, first of all, spectroscopy. When you become a chemist, you realize that the majority of your analysis is something called spectroscopy. It's where we shine a photon of light at matter. It could be paper, it could be a pure compound, it can be water. We take photons of light, photons of electromagnetic radiation, and we shine them into matter, and it interacts with this matter somehow, and then we get information out of it. So all of us were born with two detectors in our bodies to detect electromagnetic radiation. We call them eyes, we call them eyeballs. And the electromagnetic force, it's one of the four fundamental forces of the universe. You're familiar with the first one. Gravity is one of the forces. Electromagnetism is another force. That's color and electricity and all that stuff. And then we have two more, but we don't think of them because they only act at a very small atomic level. So these are the weak nuclear force and the strong nuclear force. But in this case, we have electromagnetic radiation. It gets carried by a photon. It could also interact with electrons because it's an electromagnetic component. Uh, so our eyeballs can only detect visible light, which I'm sure you must have heard at some point in your schooling, whether in middle school or high school or just watching a random movie. Visible light is the rainbow. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, right? Roy G. Biv, that was the mnemonic we learned. And it is from 400 to 700 nanometers. You need to know that. That is considered common knowledge in science. This is the question that could make you a millionaire one day. So for visible light, 400 to 700 nanometers. And then we have all sorts of wavelengths because light moves in a wave, and the wave can be a very long wave, and the wave can be a very impossibly short wave, really small. I mean, think about it. Light is in nanometers. So anything shorter than that is going to be way smaller. So there's a huge spectrum of electromagnetic radiation. We can only see 300 nanometers, and that's it. So everything you see, all the colors in your room, the colors of your clothes, your eyes, all the art that you've ever seen is only that tiny little sliver of the entire electromagnetic spectrum. I know some cats are able to see slightly more infrared. I think dogs as well. Mosquitoes can definitely see infrared. That's how they find you. They see a warm glowing spot of infrared light being emitted from your body because infrared radiation we feel as heat. If you've ever been to Universal Studios or you've ever been near an explosion, hopefully safely, but if you've ever been near an explosion, you can feel as the fireball goes up into the air, you can feel the heat on your face. Well, you're not feeling heat, you're feeling infrared light. It is also a photon, but it's not visible photon, it is an infrared photon. So if you have a wave of even longer wavelength or lower energy, you call that microwave, and we call them micro because they're usually in micrometers. They're a lot bigger than visible light, and so they're able to vibrate molecules of water. That's how the food gets heated up. That is how the guy discovered it. He was working in his lab. He had a chocolate bar in his pocket, and whenever he was working with the machine that emits the microwaves, he noticed that the chocolate would melt. So he's like, "Hey, what happens if I put it in a box and just blast it with radiation?" Well, now you can cook your chicken. So thank the guy. You can look up the story later. Radio waves. Radio waves, we don't think we think of radio as like a sound, but radio waves are photons of radio light. In other words, it's just light that has an extremely long wavelength. That's why we use radio waves for the radio, because since the waves are very long, they are able to travel long distances without getting distorted. And of course, at some point you cross the mountain and the radio station changes. I don't know if you guys still listen to the radio. I still listen to it. I hate the commercials, but I do like some of the talk shows and I do like the music choices. Of course, I don't like top 40. I'm tired of hearing Ed Sheeran's Shivers for the millionth time today. I'm not a big fan, but whatever. It used to be better. But yeah, Wi-Fi is also another type of radio waves. You're using it right now. Wi-Fi is a type of radio wave, and I'm sure you learned recently that the government and scientists are able to actually use the reflections of the Wi-Fi signals in a room to determine what is in a room and who is in a room with about 80% accuracy. So, yes, the conspiracy theorists were correct. You can be tracked physically by Wi-Fi waves because waves always bounce or get absorbed or get scattered, and if you measure all of that, well, we measure it with our eyeballs. That's what we see as color. Well, they're measuring it with their own Wi-Fi modem. That's like the eyeball of the radio waves. On the other side, we have, blue, which is the color blue, the color violet. It has a shorter wavelength than red, and it has higher energy. So blue is a stronger, more energetic color than red. Don't tell that to the Crips and the Bloods in LA. I'm sure they won't like that. But the more stronger than violet is ultraviolet. The word ultra means beyond in Latin. So ultraviolet is beyond violet, stronger than violet. If you get even stronger, you get to X-rays, gamma rays, and then cosmic rays. So we're all familiar with ultraviolet light. It cooks our skin whenever we're at Long Beach and we're walking outside without any sunblock. So we feel the effects of ultraviolet radiation, and the fact that we can see that it cooks our skin tells us that it has high energy, right? So uh, we use X-rays all the time when we go to the dentist. When we unfortunately break a bone and we have to get a cast, they usually take an X-ray. If you ever go to a chiropractor, the ones who are more legitimate actually have X-rays that they take before they start doing treatment. Um, the guy who discovered it, William Röntgen, I'm sorry, I don't know how to pronounce his last name properly. He was working with a light bulb because light bulbs had just been invented, and this specific light bulb was very powerful. And he was in a room, and when the light bulb was on, he looked at his hand and he could see the bones. And he was like, something's going on with that light bulb. So yeah, he was dousing himself in X-ray radiation without knowing it. He lived a decent life, so I don't think it impacted him too much, but a lot of people died very early when we first discovered X-rays because we had no idea they were dangerous, right? We were just discovering the fact that there's something else other than visible light. And then you have gamma rays, which is supposedly what makes Superman very powerful, right? The gamma rays from the sun interact with his Kryptonian skin, and now he has superpowers. Don't try that though. You're not gonna get superpowers. Gamma rays are very dangerous. They cause planetary bakeries. They can cook the whole planet. There's a theory that previous mass extinctions in Earth's history might have been the result of a gamma ray burst from a nearby star. You can read all about that in your free time, or you can ask me more. And then, of course, if you get to black holes where they're flat out just tearing the fabric of reality, the energy being released and absorbed is so unimaginable that, we just call them cosmic rays. Yeah, and Jose said, and Hulk. Yes, that's right. A lot of superpowers are based on gamma ray interactions. But again, don't actually ever try to get exposed to gamma rays. You're just gonna you'll just have vaporized out of existence. Don't try that. But anyway, so yeah, this is just a short overview. If you want to learn more about the electromagnetic radiation spectrum, you can, of course, read Wikipedia. You can ask your physics professors about it. And usually we have some equations. You see at the bottom, we have the speed of light, c. If you see the symbol c, it means the speed of light. That has a value of 3.0 times 10 to the negative, I'm sorry, 3.0 times 10 to the 8. 3.0 times 10 to the 8 meters per second. That is the constant c, the speed of light. This lambda, this is just the wavelength. So wavelength right here. And this symbol, which looks like a curvy V, that is mu. And so that is frequency. And so if you draw a standard wave, you see that there's like the length from this point to this point. We call that one wavelength. But also you see that it touches up and down twice. One wavelength touches up and down twice, right? And so if you have the wave that is shorter, it's going to go up and down a lot more times in 1 second than if the wave was longer. So shorter wavelengths have higher frequency, have higher energy. Low, short wavelength, high energy. Short wavelength, high frequency, high energy. Long wavelength, low frequency, because like if you're long, you're barely touching the top and the bottom of the wave, right? There's radio waves can be miles long. Imagine a wave that's like a whole mile long. It takes like a whole mile to go down and then up in the amplitude. So that one has low frequency. That one has low energy. The energy of a wave is determined by how quickly it waves. Like the faster the wave waves, the more energy it has. So this is described by this equation where the energy is equal to Planck's constant times the frequency. And since the speed of light is equal to wavelength times frequency, you can just plug in the values, you get all that sort of stuff. I don't believe you'll be expected to actually use this formula, but just in case, you should have seen this in physics in high school or here, and you can ask me more about it later. But in short, this works for all photons of the electromagnetic spectrum. Are there any questions about this? Okay, so again, at any point, any questions, feel free to unmute, ask, or you can type it on the chat. Alrighty. So again, we have the spectrum, we have frequencies, we have wavelengths. There's this concept called resonating. It's not like resonance in organic chemistry, it's just resonance in physics. They mean a little bit something different. And have you guys ever seen like the opera singers? Like they sing really high pitched and they break the glass? They'll be like, oh, shatters everywhere, right? Or maybe in Shrek, you see Fiona singing and she blows up the bird. Well, what's happening there is that the frequency of the sound waves are gonna match the frequency of the object. And when that happens, you get something called resonance, and basically the object gets vibrated at the same frequency as the wave. So in the case of the glass that shatters, the sound wave from the opera singer matches the frequency of the glass, and the glass vibrates so violently that it actually breaks. So in theory, somebody could make a wave gun that has the same frequency as a human being and basically just explode somebody on impact. I'm sure they have that somewhere in the CIA, but we're not going to talk about that. Point is, when the waves hit something of a similar frequency, they interact with it and it creates some specific effects. So for example, like I mentioned, radio waves are used in NMR, nuclear magnetic resonance, and also MRI, magnetic resonance imaging. That uses radio waves to find out specific information. So next semester, you'll use NMR to find out how many hydrogens are attached to carbons. Today, we're using IR. There is also another type of spectroscopy called UV vis, ultraviolet visible light. Basically, that's just color, right? So if you look at a carrot, it's orange. Why is it orange? Because it contains carotene, and carotene is an ene double bond. It is a UV active visible light active compound. Everything, all the colors that we see all around us are the result of visible spectroscopy. You, when you look at the world, are using visible spectroscopy to navigate the world, right? That's why if you have a food like a piece of bread and now you see that it's a little bit green, well, you're seeing something else, right? You're seeing a color. That color is telling you that there's something there. What is it? It's mold. You should not eat the bread. So your own vision is a form of UV vis spectroscopy. Really cool stuff. But today we're only going to use infrared. And as you can see from the chart, the infrared radiation is only good for telling you the functional groups. The functional groups. Is this a carboxylic acid? Is this an alcohol? Is this a ketone? Is this an ester? Blah, blah, blah. That's all IR is good for in organic chemistry. And of course, we have X-ray spectroscopy too, right? I took a class last semester called X-ray crystallography. And you take a small single crystal and you shoot a beam of X-rays at it, and the X-rays get bounced off. You do some mathematics with Fourier analysis and matrices and all that other stuff, and you can actually find out where the atoms are and exactly the length of their bonds and all sorts of crazy things. Like it's amazing that we even figured that out. Um, for microwaves, we use microwave reactors to help our synthesis sometimes. And for cosmic rays and X-rays, I mean, that just flat out like splits atoms or completely like destroys the electron shell around the proton. So that only happens in black holes, so we don't really know what's happening there. But in organic chemistry, we will be using IR spectroscopy to find out what the functional groups are. So any question about that so far? Okay, I'm gonna move on to the next slide. So what do I mean by interacting? I'm telling you we're shooting a photon of a certain energy at matter or an atom or a molecule, what exactly do I mean by the resonate? It absorbs the energy, it resonates with the molecule. So if you remember from Chem 111A, we had like n equals 1, n equals 2, n equals 3 in the periodic table. And we have like n equals 1, n equals 2, n equals 3, n equals 4. And we had something where we told you that you can take an electron and you can excite it to the next energy level. So you can take an electron from n equals 1 to n equals 2. We call those electronic transitions because it has to do with electrons. So we have electronic excitations. The electron absorbs energy, it goes up, and then it comes back down. We call that relaxation. It emits a photon of similar or lower energy. If you guys have ever seen glow-in-the-dark stars, that is a form of absorption and emission. It absorbs the light and re-emits it at a different wavelength for about 10 minutes afterwards. If you guys have ever shined a UV light at something very like highlighter color, you see that it glows very brightly. That's called fluorescence. That's also a type of absorption, excitation, and emission that happens at the same wavelength. So that's why the green gets more green, the orange gets more orange. All of this is just the electrons going from n equals 1 to n equals 3, n equals 1 to n equals 5. I don't know what exactly it is. You can calculate the energies with the equation. But in short, when there is an absorption, it has to be the exact amount of energy. This is important. This is actually the principle of quantum physics, quantum mechanics. Things can only be absorbed in multiples. So, for example, imagine you want to buy something that costs $100. If you have $80, you can't buy it because you need 20 more. If you have $40, you can't buy it. If you have $99, the store is still not gonna let you buy it. They're not gonna be like, don't worry about it unless they're unreasonably kind. You need exactly $100 to purchase something that has a price of exactly $100, taxes ignored, right? If you have $110, you could still only purchase one $100 item and you'll have $10 left over, right? So in order to make a transition, you need to have the exact amount of energy. If you have anything more or less, you are not going to go to the next level. You're not going to go to the first level. You can only go to that level when you have the exact amount of energy required. Does that make sense? It has to be the same amount of energy. So I think there's like another point here. Yep. Let me clear my drawings. Yeah, for absorption to occur, the energy must match a exact difference. And so we have also the true energy can be absorbed in, remember, you can take energy and put it into a molecule and it can rotate, it can translate, and it can vibrate. Well, it can also have its electrons excited, but that takes a lot more energy. So that only happens with like gamma rays, X-rays, ultraviolet rays. That's why it fluoresces when you shine the UV light. If it's lower energy, you don't have enough energy to create electron transitions, but you have enough energy to push the molecule translationally or to rotate the molecule. We call that Raman spectroscopy. That one measures rotational states. And of course, infrared spectroscopy, which measures the vibrational states. So a molecule can have different vibrational energy states. And if this is difficult to grasp, think about yourself. You as a human being, you have different energy states, right? You have different emotional states. You have one brain, right? But you can have a happy state, a sad state, a tired state, right? You can have a sleeping state where you're very ground state, low energy. You can have a, I just drank 5 cups of coffee and I have an exam in 5 minutes, high energy state. Molecules have different states just like that, but they don't feel. So they just vibrate, right? You could have a very low energy bending vibration. You could have a very high energy stretching vibration. And so this is basically all this is trying to tell us that higher energy causes higher excitations, lower energy causes lower excitations. And these energies that get absorbed, we call them states. So in electrons, we say n equals 1, n equals 2. We can say that. We could say ground state vibration, n equals 2 vibration, but usually we just call them vibrational states. That's a much better way to do it. Does that make sense? You guys getting the whole concept of vibration states? Just like you can have emotional states, molecules can have vibrational states. They can have rotational states. They can have energetic states, electronic states, right? Okay. So why do we use IR specifically? Well, like I mentioned earlier with the concept of the glass cup, it just so happens that the IR wavelengths resonate with the bonds. If we imagine the bond as a spring, right? So for example, here I have a spiral notebook, and the spiral, we can think of this as a spring. It's a very weak spring, right? And so look, I can, oh, it's kind of blurring it out, but I can like bend it, you see? I can bend the spring, and if the paper wasn't attached, I could stretch it out and distort it in all sorts of different ways, right? So if bonds act like a spring with masses attached to their ends, well, they're gonna vibrate in the form of a wave at a specific frequency, depending on what those atoms are. So if you're a carboxylic acid, you have different bonds than if you're a ketone. If you are an ether, you have different bonds than an amine. So that means that each one is its own unique spring. Each one has its own unique frequency. So each one is going to have its own fingerprint IR spectrum. Does that make sense? So all molecules have their own unique spectrum, and you can look at that spectrum to help you identify the molecules, right? It's just another way that we do it. And again, functional groups only. You cannot look at a spectrum and tell me this is C6H5O2. I don't know. Could be. It could also be C7,000 million H148 trillion and still have one OH, and we're only going to see the signal for that one OH, right? The bonds have to be polar. So if it's a carbon-carbon bond, well, there's no dipole change when it stretches, so it's not going to show up in the IR. So one of your pre-lab quiz questions was true or false? All compounds are IR active. False. Some compounds will not show IR vibrations. It has to meet specific conditions. The bond has to be polar, and the stretching, the vibration has to be asymmetric in order to change the dipole. I'll explain more in a bit. And of course, we also have to look at strengths, polarities. Stronger bonds are like stiffer springs. Think about the springs inside your car, in your suspension, right? You're driving on the freeway. Your whole car weighs 4,000, 5,000 pounds. And yet the springs in your car are just moving barely enough that you have a very comfortable ride. Unless you hit that pothole, right? Then you hit the pothole and you feel the whole car just right? The whiplash. And think about how much energy is that, right? You have a 5,000 pound car hitting a pothole and being compressed in the spring, and the car does not break. That's a very strong suspension that you have right there, right? So to to vibrate a stronger spring, you need more energy. That's the point. So if you have a stronger bond, like a double bond, like a triple bond, right? They're stronger than single bonds. If you have a polar bond, which is, a high polarity difference, it's a very strong bond, you are going to see more absorption of more energy. If you have a symmetrical molecule like H2, well, it's H and H. There's no electronegativity difference. There's no polarity. And also, H2 can only do this. It's a symmetric vibration. You're not going to see H2. You're not going to see N2. You're not going to see Cl2. You're not going to see I2. You get the point. So this will become more apparent as we actually practice IR. Right now, it's just a theory. I don't expect you to just understand everything right away, by the way. That's just unreasonable. Like this is your hopefully second time seeing this, and then you'll watch the videos again, you'll read a little more, and then by the time you have your post-lab quiz, you should be pretty much aware of all of the stuff to look for. So again, if this isn't immediately clicking in your head, don't worry about it. As we go on throughout the lecture, it'll make more sense. Any more questions about this one here? Okay. So we use the infrared spectroscopy. This is pretty much everything I already told you. Again, they use an example here, HCl. Think about this one. Hydrogen has a molar mass of 1. Cl has a molar mass of 35. So that would be like putting in a spring a really heavy ball at the bottom and a really tiny ball at the top. If you pick up the spring, the little ball is gonna vibrate more strongly against the bigger one compared to the bigger one against the tiny one. And so some molecules behave like that, right? H and Cl, right? Or H and F, or HBr, right? Br is very heavy, hydrogen is barely not. So HBr will have a very powerful spring bouncing energy, spring vibrational energy. So in general, we scan all of the frequencies. We start at 400 and we go to 4,000. And we don't use nanometers. We use something called inverse centimeters. We call those wave numbers. I'll explain in the next slide. But we do a scan of all sorts of frequencies, and then once that energy matches the energy of a specific vibration, it'll get absorbed, and we can measure the drop in the signal, and that's what we call a peak. So we do a whole scan, we look at where the peaks are showing up, and the location of the peaks gives us the energy of the vibrations. And the energy of the vibrations tells us what type of bond it is, what type of functional group it is. Does that make sense? And this is because, again, just like if you want to buy a $1,000 TV, you need exactly $1,000. You can't buy it with anything less. The energy matches the exact amount of the vibration. I cannot emphasize that enough. It has to be exactly the same amount of energy. That is why it is unique. That is why we can use it to identify things. Okay, so here's the instrument I showed you last week. So it's not the first time you've seen it now. Very simple to use. We just put the powder in that little tiny glass, close it, we click scan. It does the scan, it shows the IR spectra. It looks like the one below. The one you saw last week was upside down, where the transmittance of 100 was at the bottom and 0 was at the top. But also you can call it absorption and it would just be flipped. It doesn't matter. The same peaks would still show up in the same spot. What you have to do, you have to learn how to read this spectrum very specifically. In any graph, you have an x-axis, and in any graph, you have a y-axis. Unless it's 3D, then you have a z-axis. So x, y, z, you'll notice on the x-axis, on the very right, it starts at 400, and on the very left, it says 4,000, right? So it doesn't start at 0 on the x-axis. It starts at 4,000, and it goes down as you go to the right. So make sure you know how to read it. And if you come up here to the red formulas on the left, you see that there's that symbol once again, the mu. But the mu has a bar over it now. And the reason it has a bar is because, and remember, the speed of light was in meters per second. Well, look at the unit of this mu bar. It's in centimeters to the -1. It's 1 over centimeters. This mu is what is here in the x-axis. This mu bar is inverse centimeters. Are we okay with that concept so far? It's just a special type of frequency that we use specifically for organic chemistry IR analysis. We call them wave numbers. Wave numbers. So again, if you want to just supplement that with your new mu, you can use the formula E equals H times mu, and then it would be E equals H times mu bar times C. But mu bar is in centimeters, so if you ever have to use this, you have to convert back to meters, okay? It has to be in meters, not centimeters, not inverse centimeters. Fortunately, it has the same relationship as energy, right? Small number, like 400, small energy. Big number, big energy, right? Small number, small money. Big number, big money, right? Small wave number, small energy. Large wave number, large energy. Okay? Does that make sense? It has the same relationship. So just remember that. The small number is the small energy, the big number is the big energy. Okay. So this is what the spectrum actually looks like. We call this spectrum. So when I tell you to look at the spectrum, I'm talking about this graph. If it is plural, it is spectra. Because of Latin, and a. Latin words that end with are singular. Latin words that end with a are plural. So we just stole that because English is a combination of everything. And then on the y-axis, we have percent transmittance. Again, think about the word transmittance, to be transmitted, to go through, right? So if the sample is absorbing the energy, it's not going to go through because it's being absorbed. So the percent transmittance would be lower than 100 if it is being absorbed. And so that's why you see the peaks that you see here at 40% transmittance, at 20% transmittance, right? Is this making sense so far? Like, are we okay with the anatomy of an IR spectrum, how it works, what it looks like so far? And so we only measure from 400 wave numbers to 4,000 wave numbers. That's it. I'm sure there's more higher up. I'm sure there's more lower, but in general, this range is good enough for our identification purposes. We're gonna get more into detail in a bit, but this is just the basics of the IR spectrum. Any more questions about this? I think there's a question in the chat. Is the point you're trying to make about V is that normal SI units are meters? Yes, yes. And that's a good way to put it. Thank you. Yeah. So Lawrence asked me that if the point I was trying to make about this mu is that it has to be in SI units. Yes. I mean, technically, the centimeter is also part of the SI system of units, right? But it's not standardized because everything has to be in meters when you plug them into the equations. So yeah, that's a good way to think about it if it works. Any more questions? And then when you ask questions, just please make sure you address the questions to everyone in the chat. Don't be embarrassed. We're here to learn, and I want everybody to be able to see what you're asking as well. So, you know, feel free to ask. We're here to learn. This is the only lecture we get for IR. So now is the time to ask your questions. After this, we move on to our next project. Okay. Alrighty. So again, why do we talk about this so much? Because this is literally the key. A spring with two balls outside. Those balls are the atoms. The spring itself is the bond. This is the actual physics equation. This is how you can calculate exactly what frequency they're going to vibrate at, depending on, the reduced masses over here. You can plug in the molar masses of carbon, oxygen, and you can plug all of the stuff in here. Pi is a constant, C is a constant. You can calculate the energy states. We're not going to do that in this class. This is not a physics class. We're just trying to show you the physical reasoning behind this, right? And it says here at the bottom, from this equation, we see that the position depends on the strength of the bond. So it tells you here, triple bonds are stronger than double bonds, are stronger than single bonds. So triple bonds are going to have a higher wave number than double bonds than single bonds. And here's your mu bar, wave numbers. So triple bonds are stronger. Triple bonds are they're going to have higher wave number energy. Single bonds are weaker. They're going to be on the right side of the spectrum because they have lower energy, right? Just make sure you're always reading your axes. And not just that. Again, imagine you have carbon-carbon. Well, they're both the same weight. They're going to vibrate pretty symmetrically, pretty normally, right? Nothing much is really going to happen there. There's no difference. Imagine oxygen and hydrogen, like in a hydroxyl group, in an alcohol group, right? Oxygen's molar mass is 16. Hydrogen's molar mass is 1. You have a big object next to a small object connected by a bond. Well, it's like a paddle ball, right? The hydrogen's going to behave like a paddle ball, and the oxygen is the paddle. You're only going to have vibration from the hydrogen, and it's going to be very strong because you have energy with a small amount of mass, right? That's why those Honda Civic guys like to take the engines of bigger cars and put them in the small car because the car barely weighs anything. So now you have a lot of power coming out. That's why you see a Honda like speeding at 50 miles an hour on the freeway, right? That's like the top speed they can achieve. So the point is, when you reduce the weight, but you keep the energy the same, your intensity is a lot greater. So your wave number is bigger. So alcohols and H's are going to have higher wave numbers than just carbon-carbon bonds because of that difference of mass. Make sense? Yeah, there's many ways to think about this. You can find many analogies in real life about this, right? That's what we do. In physics, we call this the harmonic oscillator, the spring. It's just a fancy way of saying spring. And we figured out all sorts of mathematics about it. And we're like, look, this also behaves like the spring. So the mathematics of the spring must also be true for this system. And we call that a model. And that's how we do science in this world. We make models, we apply them into the world, and we apply the equations, and we get close enough that we have Wi-Fi and computers. All right. So no more questions about this part, right? Okay, next slide. All right. I'm going to show you some really cool actual 3D animations of this. So I'm not going to spend too much time on here. I already showed you this as well, right? You have the moving like water. You can have like a cheerleader type of like, let's go, let's go, let's go, right? You're using both of them symmetrically away from you and towards you. Or you can have like a pom-pom coming into you and then away from you, and it's like let's go team, right? Or you can have them like clapping forward together, like or maybe backwards, or some people do a somersault or whatever. That's different. That would be a rotational spectrum. Here we only care about the vibrations, right? So like I mentioned earlier, you need two conditions. The bond has to be polar when it starts vibrating, when it behaves like a spring, it changes the dipole moment. The dipole is a vector in space, so it changes the magnitude of the vector every time it gets closer or further away. And also, the two vectors have to cancel each other out. So if you look at the bottom example, carbon dioxide, the CO2, well, CO is a polar bond, right? Carbon and oxygen have an electronegativity difference. So the red arrows show you the vectors of the dipole. But because the stretch is going to be symmetric, overall, the vectors are going to cancel each other out. It doesn't matter how far away I pull them from each other. They're in opposite directions of positive and negative magnitude. So they will cancel out. You are not going to see this vibration in IR. So this is why not all compounds are IR active. Some of them are so symmetrical that you just don't see them at all. However, some molecules have some vibrations that are visible in IR, but other vibrations are not visible in IR. So carbon dioxide, again, it does have an asymmetric stretch where this bond compresses while this bond elongates, and that does actually change the vectors of the dipole moment. So when that happens, you actually do see that in IR, and you see down here, it tells you that you see it at 2350 wave numbers or 2350 inverse centimeters. You can use both interchangeably. So does this make sense? I'll show you more right now in some actual animations, but this is just like the primer for it. Okay, so next slide. Alrighty. So before we get to this, I'm going to show you the animations, and I do think I have two questions. It says, can you elaborate on the difference between the symmetric and asymmetric for a CO2? Yes. Um, so basically, think of it this way, right? Like tug of war, if you cloned yourself and you're fighting against yourself in a tug of war, ideally you would both be pulling with the same strength. Where is the rope going? The rope is not going anywhere. The center of the rope is not moving. So it doesn't matter how much energy and strength you each put into the rope. If you're both pulling with the same intensity, there is no net change. So if that were a dipole instead of the rope and the force was just the dipole magnitude, it would be canceling each other out, just like tug of war. However, imagine that instead of starting with an equal amount of rope, maybe they give the right Lorentz, a little more rope than the left Lorentz. Well, now you have the advantage of asymmetry, right? And like maybe you have less energy to pull because now there's less rope to pull, whereas the other person has to pull you and the weight of all that extra rope behind you, right? It's asymmetric. So even though it would be the same conditions, like, two Lorentzes or two carbons or two carbon oxygen bonds, the fact that they're in opposite directions, they can cancel each other out, or they can behave in such a way where they don't cancel each other out. Does that make sense? And I think it'll be more evident once we actually see the animation. So this is actually a good question to lead on to the next thing. So I am going to share that website now. Let me see. I have the quizzes open, so I have to close that first. So give me a quick second. Let's see. I'm going to stop sharing real quick, and I'm going to open up the 3D viewing website for the molecules right here. So here we go. And then back to Zoom, back to share, and here. Okay, here we go. So this is a website that I've been using for almost 10 years now because I've been a chemistry major for a very long time. Um, it's called CHEM223A. I still use it in grad school. I just used it for a presentation this past Monday, right? Very useful website. I will post it on the announcements for you guys. Somebody requested earlier, so I will do that. You can see it has organic, inorganic, structure, A level for those English people, everything else. Well, here, if you go to structure and bonding and you go to where it says molecular vibrations IR, you see that you get a drop-down list of example molecules, right? So we were talking about carbon dioxide right now. So let's just go ahead and look at carbon dioxide and then we'll get some more insights about that. Okay. So look at that. Here we have carbon dioxide. This is a 3D model, so you can actually like rotate this, play this around. You see that? Really cool stuff. That's why I recommend you use the website. So anyway, if you see the diagrams on the right, you see there's a symmetric stretch, anti-symmetric stretch, a bend, and a bend, right? So this is telling me there's going to be four vibrations, and maybe some of them are active, and maybe some of them are not active. Let's find out. So you're going to go down here. It says click to show vibration frequency list. Right here, you see the molecule has no vibration. Well, look, it says there's 1, 2, 3, 4 vibrations. Let's start with the lowest vibration. Okay. That's like it's like doing jumping jacks or something. So this is one way that carbon dioxide vibrates. And notice that the bonds are not stretching or compressing. The whole molecule is actually just bending. So this is what we call a bending vibration. There's two types. There's bending vibrations and there's stretching vibrations. Okay, stretching requires more energy. So that's why this bending vibration is at 641 wave numbers. Make sense? And so this one would be visible because the vectors are going to be adding up a little bit. You see the little yellow arrow right there? That is the dipole vector. If you see it, that means that there will be a peak. However, you can barely see it, so that means it's going to be a very weak peak of very low energy. And sure enough, it's at 641. That's a low number, right? We go from 400 to 4,000. So 641 is on the low end. Okay, let's look at the next one. 641.49. It's another type of bending. Yep, look at that. It's bending, but now it's bending in the x-axis or the y-axis. See that? Looks like it's doing like the I forgot what the name of that workout is. See, I haven't been to the gym in quite a while. But yeah, that one workout with the chest, it kind of looks like that. But again, look at the size of that yellow arrow. It's very small. That's why this is also at 641. Let's look at the next one. Look, now we jump up to 1373 and we get what's called the symmetric stretch. You see that? And so this is what we were talking about earlier. When you do this, the arrows are both going in opposite directions at the same intensity. So if you add them mathematically, like if this was +1 and this was -1, they cancel out, 0. So even though they have measured it and we do have a wave number, this is a calculated wave number. You actually cannot see this one in IR. So you can use the Hooke's law, the spring equation that I showed you in the slide to calculate the hypothetical wave numbers. But at the end of the day, real life says, yeah, that's cool. Your maths and your physics are all cool, but this is real life. You can't see that with the instrument that you used. But you can detect it with another type of spectroscopy, Raman spectroscopy. Alrighty, and then we have the asymmetric one. And look at the energy difference between the symmetric and asymmetric one. That's almost a difference of 1,000 wave numbers. You see that? And now it looks kind of like it's like pulsing a little bit. And so that actually causes a change in the magnitude in the dipole. And so that one actually does show up. And you see the wave number, it tells you that it has higher energy. So this is going to be showing up at 2438. You can see this. So again, this is just one example. Let's do another example. Let's go and do water. Since we're all familiar with water, right? You better be drinking water. Okay, vibrational spectroscopy of water. I don't think this is the one I was looking at earlier. Oh, well, it kind of works. Okay, so here's water, right? So you can have n equals 1, n equals 2. You can have v equals 0, v equals 1, right? So this is the first vibration of water. It almost looks like a bend. And this one happens at, it doesn't show. Actually, this is not the one I was looking for. I think it's this one. Here we go. Yeah, perfect. Yeah, so show vibrations. Okay, here we go. This one happens at 1711. And look at the size of the yellow arrows, right? I want you guys to notice the size of the yellow arrows because the size of an arrow in models like this, that's the magnitude of the motion, how strongly, how much is it happening? It's a lot. So this is a very intense signal. You'll be able to definitely see this one if you have an IR spectrum of water, right? And this is a bending vibration. This is not the bonds themselves being stretched in or out. This is the molecule just bending even more. All right. And so it shows you here the direction of that. And then we also have two more stretches. We have the symmetric stretch and the anti-symmetric or asymmetric stretch. Look at the energy differences, right? From a bending vibration to a stretching vibration, you go from 1711 to 3730. You see that? That's a big jump. That's almost twice as much. So twice as much energy just to vibrate water in a stretching vibration. So here's the first one, right? That's the one I was showing you, the pom-poms, right? Be careful. Somebody asked me earlier if this was a symmetric stretch. And even though the molecule itself is symmetric, you can cut it down the middle. You'll notice that the arrows are not symmetrically canceling each other out. If you were in physics and you treat those two arrows as vectors and you add the vectors together, you would get a third vector pointing in the direction of the z-axis of the water molecule. So it does not cancel out. The vectors actually add up to another vector. Therefore, even though it is happening in a symmetric molecule, you are not having a symmetric stretch that cancels each other out. So you will see this one in IR as well. And then the last one, the highest energy of them all, is this one. You see the asymmetric stretch. And notice that in this case, the molecules are actually being stretched. The bond is actually being stretched. So you can find this one at 3851 in your IR spectrum. Are we okay so far? Like, is this making sense with the animations, I hope? Let's look at another molecule. Let's add one more hydrogen bond. So H2O, let's do H3N or ammonia, right? Ammonia is just the water of nitrogen. So let's see, we go back to molecular vibrations. Let's do ammonia. Where's ammonia? Where's ammonia? Right here. So we had H2O, now we have NH3. So I added one more bond. I should have more vibrations. Well, last time we had 4. How many do we have here? 1, 2, 3, 4, 5, 6. You see that? So as your molecule gets bigger and more complex, you're going to have more vibrational states. And so a simple molecule has a cleaner spectrum. A more complicated molecule has a lot more peaks. So this is why it's important to know where to look for the peaks and where to and to look for the size and the shape and everything. So let's start with the highest energy one this time. Look at this. You have an asymmetric stretch of only 2 bonds. This one's standing still. You see that? That one is just there. It's not moving. Only the back 2 are moving, right? It looks like a little penguin walking. It's like that one penguin from Mario 64, if you've ever played that one game. Um, so there's one type of vibration. There's another one that has the same energy. Let's look at it. This one's more like a what would you call that? Like a stretch and compress? Looks like he's doing like jumping jacks too, but not really jumping jacks. Yeah, very excited penguin right here. Okay. So again, this is another type of stretching vibration. And then let's look at this one. Ah, this one's just, oh, that looks nice. I wish somebody did that to my back, just like Mr. Incredible style, just pull your back like that. This is a symmetric stretch of ammonia, right? But don't forget, ammonia is not flat. It is trigonal pyramidal, you see? So this is, even though again, this is happening symmetrically, the vectors do not cancel out because you have a vector going down in this direction. So you will see this signal as well. So you see that NH stretch right there. There's 3 of them. And then you see it goes down to 1700. So let's look at this one. See, this one is like a wag. It's like a bending, but we call this kind of motion like a wag. Let's see, if the vectors don't cancel, it's not considered symmetric. Yes, correct. The vectors of the dipoles have to cancel in order to cancel out the IR signal. Correct. So yeah. And so here you can see they definitely don't cancel, right? You can take all these vectors and you'll get a resultant vector. And then the lowest energy one, well, that's just an out of plane bending. See, they're all bending out of the plane in the same direction. So yeah. All right, let's keep looking at a few more. Let's look at benzene. Benzene is a very symmetrical molecule, but it shows up in IR. Why? Because not all of the stretching is symmetrical. That's why. So I told you guys when we had H2O, we just had 4 vibrations. We added one more bond. Now we had 6. Well, now we have a whole bunch of bonds. So we should be expecting a lot of vibrations, right? Okay. Let's see how many we have. Look at that. These are all of the vibrations possible in a benzene molecule. So let's just take a look at some very characteristic ones. Let's look at the highest energy one right away. Look at that. That's a very nice stretch right there. Very nice, equally symmetric stretch. I'm gonna say that because this is a very symmetrical molecule and it has a 6-fold rotation axis, I think this would actually not show up in IR because all of the vectors here in this case are canceling, right? These ones are canceling, these ones are canceling, these ones are canceling. So this one would probably not show up in IR at all. even though it's a very strong vibration. So it does show up in other types of spectroscopy. You can calculate it mathematically, so that's why we do know its number, but I don't think this one will show up at all. This one would show up. See, it's not symmetric. This one is not symmetric at all. And it's a little interesting, huh? It's like a water strider. Let's see this one. See here, we only have like two bonds against each other and two towards each other. The middle one's kind of not doing too much. Yeah, it's just chilling there. Yeah, really cool stuff. Let's look at the lowest energy one. Look, the lowest one is at 466. That's a bending, you see? Now the whole molecule is just being bent. It's an out of plane bend. Let's look at some other ones. Let's look at 698. Here's another type of bending. Look, this is more like a wag, like a wiggle. And it's just kind of like the Squidward dance. Here's another one. This is another bending vibration. You see, so you see how all the bending vibrations have the lower wave numbers? And if you go up to the higher wave numbers, that's when you get the stretching vibrations. I think this one's also symmetrical, but you have a higher arrow outside than inside, so this one does show up. This one is definitely not symmetrical. Look at that. And so there are classes where you kind of predict what these are and you can calculate how many exist and where they're at. But that's upper division statistical dynamics. So, we don't talk about that until much, much later. But if you are interested, there are classes. Let's do one more and then we'll move on back to the presentation. Vanillin. We are going to use vanillin in our lab in the future. So this is a molecule that you will see again. So look, how many functional groups do you see here? I see a hydroxyl, OH, this red and this white. I see an ether, right? There's a carbon-oxygen-carbon bridge. That's an ether. And I see this carbon double bond oxygen. We call that carbonyl, right? You're going to say, but it's an aldehyde. It's a ketone. Yes, but I'll explain. We call it a carbonyl. So I see three functional groups here. But my professor said the benzene ring is a functional group. Yes, technically it is, right? But it's clearly the main structure, so I don't think it's a functional group. I think it's the actual main chain itself. Again, every chemist varies. Listen to your professor. Whatever they say is correct. Okay, so we have a bunch of molecules. Sorry, a bunch of atoms, a bunch of bonds. So that means we must have a lot of vibrations. So look at the list. Look at all the vibrations that we can expect from a single vanillin molecule. So let's go ahead and start with the highest one. Look at that. So what are we seeing here? What's happening here? This is that spring I was talking about earlier. Hydrogen weighs a lot less than oxygen. So when that molecule vibrates, it's mostly the hydrogen that moves compared to the oxygen, right? Look at the size of that arrow. That's a large arrow, big magnitude. This is a very intense, high energy vibration. And remember what I told you guys about the price. You can only purchase things if you have the exact amount of money. Well, here at 3783, that photon has the exact amount of energy to vibrate only that OH bond. Notice how the rest of the molecule is not vibrating. Only the OH is vibrating. This is key because when you take the spectrum, you're only going to see a peak at 3783, and that peak is only the OH stretching vibration. And that is why we can use IR, because at the right frequencies, only the functional groups will vibrate at only those frequencies. It's very unique, very fingerprint. So you can see it right here. Only one functional group is vibrating. Let's see if I can find the other ones. Okay. I think I remember that ethers vibrate at around 1100. So I think it's this one, 1197. Nope, that is your methyl bend. You see, the methyl group is bending at 1197. Okay, let me try again. I think it's going to be at 1203 then. Nope, that's another bending. Come on, work with me here. Yeah, it's just a party. 1093? Kind of, not really. 985. I can't seem to find the carbon-oxygen single bond bend here. I think it's there. It's kind of like being bent, but like I think the whole molecule is also interacting with it. So I guess the ether signal in this molecule would not be very distinguishable. That's what we can conclude. Let me see if I can find the carbon double bond oxygen. I know that one vibrates at around 1700. So let's see, 1699. Nope, that's the rest of the molecule. 1848. Yep, there it is. Look at that. So even though you see some of the molecule vibrating, you can see right there that this carbon oxygen is the main vibration of this motion right here. And this happens at 1848, which is characteristic of carbon double bond oxygens. Double bond oxygens vibrate between 1650 and 1850. So within that range, if you see a strong peak, most of the time you're gonna have a carbon double bond oxygen vibrating. And also notice too that like this vibration does affect the other parts of the compound slightly. So sometimes you see extra peaks here and there. We don't use all of the peaks. We only use very characteristic peaks. Let me see if I can find a few more. Oh, look at this one. Looks like a boxing glove. This is also very characteristic. You're gonna see this in every spectrum. Every organic molecule has carbon-hydrogen bonds, right? Because it has carbon, so it must have hydrogen because it's organic by definition. So this is called an sp3ch vibration. This is very strong, and this shows up in every IR spectra. So you need to know how to look for it, but just pointing it out is nothing. It's like, of course, you should know that, right? So make sure that you know how to distinguish this from other vibrations of all the other functional groups. So I'm gonna go back to the presentation now. Are there any questions about anything we observed, the animations, the vibrations, the wave numbers? There's other websites you can use besides CHEM223A. Like you can go on Google, type in Purdue IR vibrations, and you'll get this website. You can rotate them around as well, but I kind of like CHEM223A a little bit better. But you can see here, it tells you the wave numbers. It tells you if it's IR active or IR inactive. So yeah, look at that. We predicted that this symmetric one would be inactive, and sure enough, it's IR inactive, right? So you can see here, test yourself and kind of just visualize the concepts a little bit more. It says, does sample phase affect what the spectra looks like, difference in peaks? Sometimes it does, sometimes it doesn't. So for example, we're going to see that hydrogen bonding, which happens in liquids, can change the vibrational frequency of the compounds and the bonds. So maybe instead, I mean, that would be a cool experiment, right? Take an IR spectrum of water in the form of ice and take an IR spectra of water in the form of liquid and then see if they're the same. That's actually an interesting question. As far as I know, there shouldn't be too much of a change if it's a powder or if it's a liquid. But in general, we usually take IRs of solids. Um, Good question. I'll look more into that and I'll have a better answer for you next week. Alrighty. So yeah, you can come over here and you can see, for example, methane, right? Here's all the vibrations of methane all at once. And it tells you which are active and which are inactive and where you can expect to find them in the IR spectra, sorry. Alrighty. So there you go. I'm gonna go back to the presentation now. So give me a quick minute. Stop sharing and then share and then back to the PowerPoint. Okay. So again, any more questions? Anything else that you guys want to know before we move on? Now we're gonna switch into actually analyzing the spectra. So what we do is we look for three things. We look for the wave number, where on the x-axis is the peak located, right? When you start talking to me about peaks, I want you to give me numbers. Tell me, for example, if you were gonna reference this peak right here, what would you say? Where is it located on the x-axis? Okay, we got someone in the chat. 3,300. Yep, 3,300. Let's see, one, two, three. Yeah, about between 33 and 34, right? So you could call it 3,300. You could call it 34. Maybe we could call it 3,350, right? I don't know. Usually, some charts give you exactly where the points are, but you still have to be able to visually look yourself and make those descriptions. So if you were to tell me, hey, I have a question about this peak, which one? You need to tell me the peak at 3,300. You can say 3,300, 3,300 wave numbers, 3,300 wave numbers, 3,300 inverse centimeters. They all mean pretty much the same thing, but specifically we say 3,300 wave numbers, 3,300 centimeters inverse. But just know that you need to be able to talk about these, right? So what would you say this peak is at right here? If I were to tell you, where is this peak? Yep, 1500 roughly, right? As long as you can estimate reasonably, you can't look at that peak and tell me 2000. No, 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 man. 2000 is way over here. That's nowhere near that. So you have to be reasonable, right? Estimates are okay, but be reasonable about it. Okay, so we look at wave number, x-axis, then we look at shape. So I'm going to use another one for shape. I'm going to use the color red. So look at this one at 3300. How would you describe that shape? Would you describe it as sharp, broad, narrow? Would you describe it as smooth? Would you describe it as, yeah, what is that shape? The peak at 3300. How would you describe it? Okay, somebody said looks a bit smooth. Okay, you're right. A little smooth, right? Broad, sharp, narrow. Broad, yeah, it's a little broad, right? How can you tell if it's broad? Well, look at the x-axis again, right? This seems to start around, I don't know, let's say 3100, 3150. Like it seems to start around here and it seems to end around here, right? So that's a difference of, let's see, 31, 35, 36. That's a difference of about 500 almost, 500 wave numbers. That's pretty broad. That's a pretty broad peak, right? You could also just see it visually yourself. Look at this. It spreads out over quite a bit. So I would call this peak broad. What would you call this peak right here? How would you describe that peak? Sharp, right? Sharp, very narrow. The proper way is very sharp. That's what we say. VS, very sharp, or we just say VS, very sharp, right? Sometimes you have like a combined peak. So like these peaks right here, you see it's kind of like one peak, but also it kind of splits off at the bottom. So we can just say multiple peaks, multiple sharp peaks, right? A broad signal that has multiple sharp peaks at the bottom, right? We can start using this type of language to describe the peaks in our spectra. So we look at shape, we look at wave number, we look at intensity. I'm going to use pink for this one. The intensity is the y-axis, the percent transmittance. The closer to zero, the more intense. So for intensity, we use words like weak, medium, strong, very strong. So for example, once again, this peak here at 3300, what would you describe that in terms of intensity? Is it a weak peak? Is it a medium peak? Is it a strong peak? Is it a very strong peak? How would you describe this? Right? Strong. Yeah. Strong peak. If you say very strong, it's also very strong, right? I mean, look at the percent transmittance. Only 10% of the measured IR radiation is being transmitted through the compound. That means 90% is being absorbed. That's a very strong absorption, right? It it's subjective as long as you get the gist of it. Again, you can't call a very strong peak weak. That's just flat out wrong, right? You can't call something that's very strong medium, right? Medium would be 50%. Well, 10% is not 50%, right? There's a clear distinction there. But I mean, if you're like confused between strong and very strong, that's more like, well, again, be reasonable about it. But yeah, yes, if it's closer to zero, it's stronger because remember, we're measuring percent transmittance, right? How much of the light is getting through? If 0% of the light is getting through, if 0% of the light is being transmitted, that means 100% of it is being absorbed. And when you absorb that light as a molecule, that's what you use to fuel your vibrations. So yeah, you will see some IR spectra, instead of percent transmittance, it has absorbance. And that's why they're upside down. But it has the same peaks at the same wave numbers, they're just flipped. So you still have to be able to tell the wave number, the shape, and the intensity, whether it's in percent transmittance or it's in absorbance. But in this case, for percent transmittance, the closer you are to zero, the more intense the peak is. Yes. Okay, good questions. All right, so again, how would you describe this very sharp peak at 1500? What word would you use to describe that intensity? Medium. Yep. You can call it medium. I think we call it medium strong, right? I mean, there's no real set of standards here. It's very subjective, of course. Um, as long as we see that you're being reasonable, yeah. So the question is, so the sharp peaks on the right are strong. Well, they would only be strong if their transmittance was below 50. So most of these peaks, for example, this one that's very sharp, this one is at about 30. So that one I would say is kind of strong. That one I would say is strong. The ones around 900, 800, even though they are sharp peaks, they are not strong because they are at 75% transmittance. They are not being absorbed a lot. So, just think of the height. The longer the peak, the more strong it is, right? Just look at the size of the peak. If it's a tiny peak, obviously it's very weak. If it's a very large peak, obviously it's very strong, right? Then just look at the shapes either. So there's the shape, broad, sharp, there's wave number, x-axis, and there's intensity, y-axis. Any more questions about this? Okay, so this is really all we need to look at, and we do not look at every single peak, and you will see that pretty soon. Each functional group has its own iconic characteristic peaks. You need to know what they are. So if there's no more questions, I will move on to the next slide. Here we go. All right, so here it is, the secret you've all been waiting for. We know where they are. We know roughly where to find them, right? Remember, single bonds are weaker than double bonds. So single bonds are going to have lower wave numbers than double bonds and triple bonds. So most single bonds are going to be found on the right side of the spectrum. There is this region called the fingerprint region. Basically, it's all of the not very significant bends and stretches of the molecule. Some chemists say that it is at 1000 and below. I was taught that it was at like 1000 and below because you still have some characteristic stretches at 1100. But this book or this section teaches you that it is below 1400. Stick to whatever your professor tells you is the fingerprint region. But regardless, we don't really look at the fingerprint region first, right? Because there's a lot of things that vibrate at those frequencies. It's kind of hard to distinguish them. So we actually go and look at the higher wave numbers first because those are more characteristic, those are more telling, they're more iconic. And so if we go to the higher wave number, you see on the x-axis, we have 3500 to about 2700. You see you have your polar bonds, right? Carbon, hydrogen, oxygen, hydrogen, nitrogen, hydrogen. Those are polar bonds. And you might think, well, I was taught in general chemistry that carbon, hydrogen is nonpolar. Well, there is an electronegativity difference, right? It's not significant enough for us to call it polar when we're talking about structure, but real life, as long as there's a difference, it has a change in the dipole vector. So there is going to be a signal. It might be a very weak signal, but it's there, right? So in this case, there are signals for carbon hydrogens. There is an electronegativity difference. Sorry. There's also a mass difference, right? Carbon and hydrogen, carbon weighs 12, hydrogen weighs 1. So that's another factor that affects your vibrations. So those higher energy bonds are in the higher wave number section. And then you have your triple bonds between 2000 and 2500, carbon-carbon triple bond, carbon-nitrogen triple bond, carbon-oxygen triple bond. They do exist, very rare. Those would be located around that region. Your double bonds are between 1600 and 1800. So this is where you get your carbon-carbon, carbon-oxygens, carbon-nitrogens. And, as we go through these examples, you'll kind of see what exactly all of this stuff means as well. But we know where they are, right? You're never going to find a carbon-carbon double bond at 400, right? You're never going to find a carbonyl at 4000. That's just something else is going on there, right? So this is another thing that we use, right? We look at the shape, we look at the size, we look at the intensity, we look at the patterns. This is all pattern recognition. Where have I seen this before? And if it looks like this, I should expect it in a similar place. So any questions about the regions? Okay. So Let's start with the most basic type of compound, the alkane, the alkene, and the alkyne. This is strictly just a carbon-hydrogen bond. It could be a carbon-hydrogen bond, carbon-carbon double bond, carbon-carbon triple bond, right? There's multiple perspectives to look at this. First of all, look at the spectrum on the top right. You'll notice that it's relatively clean. There's not a lot of peaks, right? There's only two really major areas that have peaks. This right here at 3,000, a little bit below 3,000, I would say between 28 and 3,000, this whole region right here. Have you guys ever been to a cave or have you seen pictures of a cave and you have like all the stuff on the top of the cave? Those are called stalagmites. Oh, I don't know what happened there. Hold on, give me a second. Resume slideshow. There we go. Okay, I don't know what happened there. Sorry about that. So you have your little peaks at the top of the cave. Those are called stalagmites. And that's what I like to call this group here. I like to call them the stalagmites. This is a carbon hydrogen sp3 stretch. I have a question in the chat. They do look like ice cones. Yes, yes. Ice cones, you could think of icicles. That's a good one too. I like stalactites, right? It makes more sense for me. But whatever works for you, call it what you want. But this right here, this is the carbon hydrogen sp3 stretch. What does that mean? That means that you're always gonna see this. This is everywhere. Every organic molecule has a carbon hydrogen bond, right? Methyl groups. Alkanes are all sp3ch bonds. So every organic molecule that you are going to analyze is going to have something in this region. And I'm going to ask you a million times about it because this is everywhere. You cannot look at this and say, I'm confused. I got nothing else to go off of. I'm going to call these OH. I'm going to call these carbon oxygen. No, 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 no. These are very iconic CHSP3 stretches, the stalagmites. They are always going to be present in almost every spectrum that you are going to see. So you need to know when to consider it and when to ignore it. We know that triple bonds are stronger than double bonds, and we know double bonds are stronger than single bonds if you look at the bottom. So since alkynes, triple bonds are stronger, they should have a larger wave number, and they do. Look, 3,300 wave numbers for triple bonds, 3,100 wave numbers for double bonds, 2,900 for single bonds. In other words, the more S character you have, the higher your wave number. So this is higher wave number over here, higher wave number, and over here would be lower wave number, lower mu bar. Right? And this is just another perspective, right? I like to look at it from the perspective of bond type. I know triple bonds are shorter and I know they're stronger, right? Remember when we did that experiment on day one and it asked you about rotation about the single bond? Well, the single bond is weak. You can rotate it, no problem. But as soon as you have a double bond, you can't rotate it. It's a lot more stiff. So to vibrate it and bend it, you need more energy. Imagine a triple bond. Well, that's a lot stronger. So you need a lot more energy. That's why that wave number is higher. So if you see a spectrum and you don't see very much going on, and you see the stalagmites, you probably have some sort of hydrocarbon. What type? Well, again, the triple bonded sp carbon, it has a higher wave number. So you do see a peak at around 3,300 right there. It's a weak, sharp peak. Weak, sharp peak at 3,300. And you also see the weak, sharp peak over here at around 3,100. This is also a weak, sharp peak right there. And then over here with the alkane, it just blends in with the whole broadness of the other signals. So you don't see that peak right there. So this is how you can tell if you have a double bond or a triple bond in your hydrocarbon chain. Does that make sense? You look at the characteristic peaks. You don't have to look at everything. And I think some of you might have a question, which might be something like, well, what's this over here? I'm going to use green. You might say, well, what are these over here? Well, they're at 1,500. These are probably some sort of CH bending going on over here somewhere. Which one? Is it this one? Is it, I don't know, man. There's a lot of peaks sometimes. We only look for one or two, maybe three, and that's it. The rest we kind of just ignore because we cannot really know exactly what they are. We're looking for characteristic peaks. We're looking for iconic peaks. Okay? So then what do you consider characteristic peaks? The weak sharp pearls to peaks to the sides. Yes, exactly. Yes. If all you see is stalactites, alkane. If you see the stalactites with a little peaked a little to the left, there's probably a double bond or a triple bond, depending on how close it is. You'll notice that the spectra for the triple bond has the peak a little further away from the stalactites compared to the alkene. They're almost right next to each other, right? Yeah. So what do I consider characteristic peaks? The more spectra that you practice with, the more you see the patterns of the characteristic peaks. Okay. All right. I'm going to move on to the next slide. So here's octane, plain old boring alkane. So what do we see here? Well, again, take a look at the higher wave numbers first. So look at between 28 and 3000. You see the stalactites are showing up already once again. So this is your CH3 stretching. Octane is all sp3 carbons. So this is your sp3 CH stretching, all of these. There's probably a CH2 sp3 stretching right here. So this would be like a methylene, we call it, CH2 sp3. But which one is it? Which exactly is it? Man, I don't know. They all blend in together. We just have to be able to say, look, these are the stalactites that I know that's everywhere. Is there anything else? Well, it's a pretty clean spectrum. There's hardly any peaks. So, and again, at around 1500, we get our CH bendings. I don't see much of anything else. This one here is probably another CH bend of some sort. But I mean, that one's in the fingerprint region. We're not really gonna pay much attention to it. It's also very weak. I mean, could be anything really. So the absence of any other signals except the characteristic CH signals tell me this is just a plain old alkane. Make sense? So I guess you could call the stalactites a characteristic peak of hydrocarbons. Okay, so let's look at another type of hydrocarbon. What happens with aromatic rings, right? They are also made of just hydrogen carbon. So what happens there? Let's see. Here we have toluene. You see the structure is on the bottom left. And now we have alkenes, carbon-carbon double bonds, but we also have aromaticity, right? Where the ring is delocalized and has a certain number of electrons inside the system. Well, you see the stalactites are still present roughly at the same location, right? Between 2800 and 3000. You see they're still there, but you'll notice their shape is a little different. Well, they're less intense. They are weaker. Why are they weaker? Because double bonds are stronger, so you need more energy to vibrate them. So it might absorb some energy, but not as much as a single bond. That's why the intensity is lower. Make sense? And also, look how much more sharp the signal is. You have a very specific aromatic carbon-hydrogen stretch. So that would be like this one right here. This carbon-hydrogen stretch would be right there, that peak. You still have your standard CH3, sp3 stretches from this methyl group, but again, they're a lot weaker compared to the other signals. When you have an aromatic ring, you get these combination bands. They don't always look like that, but you have extremely weak, like little hills up here between 1600 and 2000. They don't always show up, but if you're suspecting an aromatic ring, this is something that you can look for and be like, oh, well, I know that shows up with aromatic rings. So, I mean, there's very likely one. And also, you have a characteristic aromatic carbon-carbon double bond stretch at around, let's see, that's like around 1475, I believe. Right there. Very sharp. Aromatic peaks are very sharp because, again, the spring is stiffer. So you need a very specific energy to vibrate those. So if you see a spectrum that doesn't have a lot of stuff, has a little bit of hills on the top, the signals are weaker but sharper, you most likely have an aromatic ring somewhere in there. And you can see this is methyl benzene toluene. You can see the structure is down here. There's nothing else, just carbons and hydrogen. So, it's still a relatively clean spectrum, but it does look a little sharper. So any questions about this one right here? Okay. Moving on to the next compound. Carbonyls. Okay. I do need to take some time for this one. So you've noticed by now in organic chemistry that we are very specific with our language. If you ever get the pleasure of watching two organic chemists argue with each other, your mouth is going to drop to the floor because you're like, how can you possibly use language like that? How can you possibly use technical terminology so fluidly? Like obviously they're speaking English, but it sounds so amazingly insane when they talk. And they'll argue with each other too, like passionately. So the point is, we speak very specifically. So in class, you do get points off when you're not specific. I always ask you to be very specific. It's better to be more specific than not. Of course, make sure you have enough time to answer your questions, but we're very specific with our words, right? Organic chemistry as a second language. So when we talk about carbonyl, I'm talking strictly about this. Carbonyl is equal to this. It's a carbon double bond oxygen. Notice that there's nothing attached to the carbon. It's just a carbon double bond oxygen. This is not an independent structure. This is a component of a larger structure. But when we say the word carbonyl, I am specifically and strictly talking about a carbon double bonded to an oxygen. So you have to use that word. You have to say the word carbonyl when you are referring to the carbonyl stretch. You can't say this is a ketone stretch because you don't know if that's a ketone. A ketone contains a carbonyl, right? Functional groups contain carbonyls, but they each have their own name. So it's like the first name and the last name, right? Like who are you? Like the ancient Spanish conquistadores, right? Like what is your name? I am Juan Ponce de Leon, right? They have like their long last name. Or like if you've seen the Lord of the Rings, right? Like who are you? I am Aragorn, son of Arathorn. Like that is like who are you? I am carbonyl of a carboxylic acid. Who are you? I am carbonyl of an aldehyde. Who are you? I am a carbonyl of a ketone. You see how I'm using my language? The carbonyl can be included in other functional groups, but when you say the word carbonyl, you're strictly talking about carbon double bond oxygen. Okay, so when you are telling me this is a carbonyl, you better tell me this is a carbonyl. If you tell me this is an ester, I'm going to tell you which one, the carbon double bond of the ester or the carbon single bond of the ester. You need to be specific. We have specific words for this. So here is the family of carbonyls. Let's meet them. Happy family reunion. Ta-da! All right. So all of these are functional groups that have their own names and they all contain one carbonyl. Are we okay with that concept? You learned a new word today. That is carbonyl. Carbonyl is like iconic. It's like Bugs Bunny. It's like SpongeBob. Like whenever you do IR spectra, if you learn nothing else, you should at least know that's a carbonyl peak at 1700, right? The mitochondria is the powerhouse of the cell. Well, the carbonyl is always at 1700. Very strong, intense peak. Okay. And so remember that the signals depend on polarity and it depends on the atoms attached to the carbon. So some carbonyls have higher wave number than others, even though they are all carbonyls. This is not absolute. This is not 100% exact. For example, you might find a ketone at 1760. You might find an amide at 1715 under the right conditions, right? It's that's why we give you the range. I like to say look around the 1700s plus minus 50. Carbonyls are always found at 1700 plus minus 50 wave numbers. So look at the carboxylic acid. You have a dipole in the direction of the oxygen, and you have a dipole in the direction of this oxygen, right? So that means that you should have more energy because it's a very polar bond happening right there. And sure enough, look at the wave numbers. 1710, 1780. They're the highest of all of the carbonyls. The next one would be ester, right? Very similar to carboxylic acid, but instead of an oxygen hydrogen, now you have an oxygen carbon. So the wave numbers are still very high, but they're smaller overall than the carboxylic acid, right? And look at the amide. Also has two dipoles, but one is from a carbon-nitrogen bond. That's a lot weaker, so the wave numbers are smaller. There's also another carbon-nitrogen bond over here that is withdrawing more electron density, so that also further weakens the bond. Look at the aldehyde. That's just two dipoles, but one of them has to do with a very light atom to a very heavy atom. So you get a wide range. Look, aldehydes can be anywhere from 1690 to 1740. Ketones, well, a ketone looks just like a carbonyl, right? Well, yeah, it contains a carbonyl. This is the carbonyl of the ketone. But it is a ketone because it is connected to an R1, R2. It is connected to two other carbons with more stuff. The carbonyl is not by itself a molecule. It is the part of the molecule, right? Just like this is my hand, right? This is not Eduardo Vitae. This is a part of Eduardo Vitae. The carbonyl is a part of a ketone, right? The carbonyl is a part of an aldehyde. So again, think of it like a last name. Like, well, who are you? I am a carbonyl of a carboxylic acid. Who are you? I am a carbonyl of an ester. I am a carbonyl of an amide. You have to talk like that. You have to, when I tell you be specific, if you don't talk to me like that, I'm not gonna have any idea what you're saying because there's other groups here. Are you talking about the OH of the carboxylic acid? Are you talking about the CH of the aldehyde? Be very specific with your words. And so we're gonna go through some examples right now of different types of carbonyls in different functional groups. But are we okay with the distinction between functional groups and the carbonyl? Okay, so let's look at some examples. All right, so here we have two different carbonyl functional groups. One is a ketone, one is an aldehyde. Let's take a look. So again, we start with the higher wave numbers. So let's look at the large wave numbers. We have our stalagmites, right? Very standard. This is everywhere. We look at it and we're like, okay, that's cool. What else is there, right? Let's see. At 1718, we have a very strong, sharp peak. You see that? Right over here. Very strong, sharp peak. The transmittance is almost zero. It almost touches the floor, the axis, the x-axis. This is what a carbonyl stretch looks like. Very iconic. Look at 1700 plus minus 50. If you see a signal that is very strong, almost to the floor, that is about 90% of the time a carbonyl signal. So look at the bottom one, butyraldehyde, right? You have this carbon double bond carbonyl, and look, it's at 1720. It's almost touching the axis as well. So this is your carbonyl CO stretch. Are we okay with this so far? Now, how do you know which is which? How do you know if one's a ketone or one's something else? Well, you look at the structure, right? Remember, you cannot determine the total structure based on the IR spectra. You kind of have some idea what you're looking for. So in this case, if you look at the aldehyde, I have a CH bond that is connected to my carbonyl. You see that? Well, that CH bond is a lot weaker because of that electronegative oxygen hogging all the electrons towards itself. So that CH bond is a lot weaker compared to a standard CH bond. So if you look at your stalagmites right over here, you'll see them. These are your regular run-of-the-mill sp3 CH stretches. But if you look at these two signals, they're a little bit weaker signals, right? They're around 40% transmittance. Those specifically are an aldehyde CH stretch. The aldehyde CH stretch, this is how we call it, aldehyde CH stretch. It's usually lower in wave number than the standard stalagmites. You don't always see it because sometimes it's just very weak and sometimes it blends into the broader signal. But if you're suspecting that you have an aldehyde and you want extra confirmation, you can look at those peaks at 2820 and 2720. Those are the peaks for the CH aldehyde stretch. Very characteristic of aldehydes. And that is one way that you can tell whether you have a carbonyl of a ketone or a carbonyl of an aldehyde. You look for more signals. Are we okay with this so far? You have to know the carbonyl. Like if you learn nothing else, please learn the carbonyl. Learn that the carbonyl is a very strong signal at 1700-ish. Okay? Okay, next slide. Conjugation. Well, we've talked about alkanes, alkenes, and we've talked about carbonyls. Sometimes you can put them together. So you're going to see this word a lot in organic chemistry and in biochemistry when you take the class. This word is conjugation. Conjugation is just a repeating system of double and single bonds. So if you have a double bond, then you'll have a single bond. You'll have a double bond, single bond, double bond, single bond, double bond, single bond to infinity. You can if you want. That double bond can be a carbon-oxygen double bond. So you can have carbon-oxygen double bond. Whoa, that's a terrible oxygen right there. There we go. There we go. Carbon-oxygen double bond, single bond, and then just regular double bond, regular single bond, regular double bond, regular single bond, and then carbon-oxygen, and then single bond, and then double. This is also a conjugated system. That is what we call it. Again, we're very specific with our words. This is a conjugated system. It has conjugation. So when a molecule has conjugation, it creates resonance. When you have resonance, your double bond behaves sometimes like a single bond, sometimes like a double bond. So 2 plus 1 equals 3. If you average it out, divided by 2 is 1.5. So actually, it's like a bond and a half, right? So double bonds are stronger than single bonds, but then in between, you have your bond and a half that is created by resonance. You can see it right here. You have like the hybrid resonance structure. That weakens the bond. That weakens the double bonds of the alkene. That weakens the double bond of the carbonyl. And so that lowers the wave number. If you look at this example down here, we have a regular ketone carbonyl. We can find that signal at 1720. As soon as we create it into a conjugated system by alternating it, see, we have double bond, single bond, double bond. We have created a conjugated system that is going to delocalize the electrons. It's going to spread them out throughout this whole region. That means that it's going to make the bonds weaker. And sure enough, you see that the wave number is lower at 1680. So if you have conjugation in your molecule, whatever your wave number you're expecting, it's going to be a little lower. And this is why I'm telling you that those numbers that I showed you from the earlier slide are not absolute. Ketone without conjugation is at 1720, but if you have a carbonyl of a ketone in a conjugated system, well, that same ketone is now at 1680. It's not absolute. Overall, this is still very close to 1700. You know, it still falls within the plus minus 50 rule. So just make sure that you look at your structure too. And again, you don't go into IR blind. You have some idea what you're looking for. So you should know if you have a conjugated system. Any questions about this? Okay. So next slide. Alcohols and phenols. Okay, now we're talking about another one, right? So phenols are just a type of specific group that has a benzene ring with an OH at the end. So you have your benzene ring right here, and you have your OH right there. Well, even if you're a phenol, you still have an OH, right? So in general, it's the OH bond that we're looking at in these stretches, right? That OH bond is the characteristic one that we are looking for. So how do we see it? Where is it at? What does it look like? I'm going to use pink. You see here at 3300, we have a broad, strong signal. This is your OH stretch. Remember in the animation I showed you earlier, you had like that hydrogen and it was beating up against that oxygen. That is this signal right here. That is the OH signal. It's very broad. It's very strong. I mean, I wouldn't say very strong, but definitely strong, right? It's at 25%. That's definitely strong. But it's broad. It goes between 3200 all the way to about 3500. So between 3200 to about 3500. And it's always very smooth. If you see a signal that looks like that, like a big smooth drop, then that is most likely about 90%, 85% of the time an alcohol. Very, very distinct. Now, why is it so broad? Why is the signal so broad? Remember that OH can hydrogen bond, right? OH NH and FH, they can all hydrogen bond to an oxygen, to a nitrogen, and to a fluorine. When you're hydrogen bonding, you are further restricting the motion of the bond. You're making the spring stiffer, even more stiff. So you need even more energy to vibrate it. That's why the OH group has a higher wave number. But also, not all of the OHs are hydrogen bonded at any given point. Some of them are, some of them are not. So you get like a Gaussian distribution of some sort, where the lower ones are not hydrogen bonded and the higher ones are hydrogen bonded. And then you get those in betweens that are partially hydrogen bonded and partially not hydrogen bonded. So that's why you get this larger, broader distribution of the signal. So this is very iconic of an OH. If you see this signal at that region, you should be thinking that's an OH right there. But note, we also look at the shape and the size. It's a strong signal. It's a strong signal. It's a broad signal. Okay? Any questions about the OH? All right. And then, in general, if we have an OH, it's bonded to a carbon, right? So it's COH something. This carbon-oxygen bond is also polar and it also vibrates. So we do see that signal at around 1100. Carbon-oxygen single bonds are usually between 1200 and 1000, but most likely they are often around 1100. Again, some people would consider this the fingerprint region, so sometimes they don't look for it, but you should just know where they are because ethers are also carbon-oxygen bonds and they show up in the same region. So you kind of start seeing the patterns of where the bonds are located in terms of wave numbers. So any questions? What about this in the green? What are these? What's that in the green? Nope. There is no carbonyl in this example. It's one hexanol. Draw it out, right? This is a common thing I observe every semester. People just start shouting out carbonyl here and there. That's okay. We're learning, right? But just be careful because if you're gonna tell me that you have a carbonyl, I'm gonna point to 1700 and I'm gonna say, where is the carbonyl signal? It's not there, right? Alkane, that's right. These are your stalagmites. Remember, they are always there. These are present in every spectrum right here. So these are your sp3ch stretches, your stalagmites. Always there. You need to know that they are not something else. You cannot confuse that with another functional group, or that's how you lose points. So yeah. And make sure that if you're gonna say a carbonyl, before you tell me something is a carbonyl, answer this one question for yourself. Is it at 1700 plus minus 50? If the answer is no, then there's no possibility that it's a carbonyl. Is the signal very strong? If the answer is no, then it's not possible that it's a carbonyl, right? So while this signal at 28, 29 is very strong, it is very far away from 1700. It cannot possibly be a carbonyl. So make sure you know. Make sure you know what's what. All righty. Let's move on to the next slide. Carboxylic acids. Now we're getting to compound functional groups. A carboxylic acid is made out of two functional groups. It is a hydroxyl and it is a carbonyl. So this is why we have distinct names because we need to be able to talk about three different things and their components. So the carboxylic acid, you'll notice, has a very broad signal. It starts at around 2500 right here. You see, it's like you get this really wide signal all the way to 3500. You see, it goes very, very broad. Usually there's a 1000 wave number spread. When you have a hydroxyl, this is the OH, a hydroxyl of a carboxylic acid. This is a hydroxyl. And also, you'll notice, what is this right here? What is this really sharp bottom peak at around 3000? What are those? What are those peaks right there? We've been seeing them everywhere. They're in every molecule. Can't move on until someone gives me an answer. What are those peaks right there around 3000? CH, that's right. Alkyls, that's right. Those are the stalagmites. They are always present in all spectra. Always. You need to know where they are. The stalagmites are always sp3 CH stretches. Sometimes it's sp2, but most of the time it's just sp3 CH stretches. The OH hydroxyl signal, it overlaps the stalagmites. So it creates this weird looking, we call it the wizard's beard. So let me clear the drawing real quick. I don't know if it got cleared, but we call it the wizard's beard. So you could think of this as like a wizard, like right here you have like the wizard smiling, and then this is like the beard of the wizard and the hat's up here, or Santa Claus, if you will, right? So if you see a very broad IR signal, about 1,000 wave numbers broad, and it looks like a weird beard of a wizard or Santa Claus or whatever, Eminem from Machine Gun Kelly's diss track, um, you know that you have a hydroxide that is very likely from a carboxylic acid. How do you confirm it? You have to confirm it by looking for the other component, the carbonyl. So again, if you're looking for a carbonyl, go to 1700. So here's 1700. Is there a very strong peak present? Yes, there is. Look at it. So this is your carbonyl from your carboxylic acid. So this is your carbonyl from carboxylic acid. You have to use that phrase. This is the carbonyl of the carboxylic acid. This is the hydroxyl of the carboxylic acid. A common mistake that people make on the quizzes and on the final exam is that they'll point to the hydroxyl signal and they'll say, that's a carboxylic acid. Which one? Is it the carbonyl of the carboxylic acid or is it the OH of the carboxylic acid? The whole thing doesn't have one signal. It's made of multiple bonds and each bond has its own signal. So you need to be very specific. This is the carbonyl of the carboxylic acid. This is the hydroxyl of the carboxylic acid. Very specific words. And again, sometimes we don't use all of the signals. I'm going to use pink now. What's this over here? I don't know. What's this? What's this? What's this? What's this? What's this? Honestly, all I saw was a carbonyl and a hydroxyl signal. And that's enough for me. That tells me I have a carboxylic acid. The rest, I'm going to use other methods to figure out what else is in there. But remember, IR tells us about functional groups. So I found my functional group signals. I can move on to the next thing. You don't always look at all of the signals. You look for the characteristic signal. Any questions about this? Okay. So moving on to the next slide. All right. Ethers. An ether is just a carbon-oxygen-carbon bridge. So here we have dibutyl ether. So we have butyl, 4 carbons, 1, 2, 3, 4, and then we have an oxygen, and then we have 4. 1, 2, 3, 4. So this is dibutyl ether. There's only carbon and hydrogen and carbon and oxygens, nothing else. So the spectrum should look really clean. And sure enough, you don't see many peaks. So it's very easy to tell. So again, we start with the higher wave numbers. I'm going to use green. What are these? What are those signals right there? They're everywhere. All molecules have them. What are these signals here? Yep. But be specific. When you say alkyl, what kind of alkyl? Alkane, alkene, alkyne? And look at the structure too, right? Again, you're not going into this blind. Look at your structure and use that information to justify your signals, right? It's an alkane because dibutyl ether is only sp3 single bonds. There's no double bonds, there's no triple bonds. So these are your sp3 CH stretches. You notice how this keeps coming up in every single example? That's because every organic molecule has CH bonds. That's why. So, well, that's cool. It doesn't really help us. So let's look at the next things. I have something here happening. I have something here. I think we've learned by now that these are the CH bends. So we kind of just ignore them. They don't really tell us much. Oh, but look, I have a signal that looks very similar to a carbonyl, right? People might look at this and be like, oh, I'd recognize that shape. That's a carbonyl. Well, again, go to 1700, right? Wait, I'm in the wrong place. 1700 is over here. Go to 1700. Is there a very strong peak at 1700? No. It looks like it, but it's not at 1700. This is not a carbonyl. This is just a carbon single bond oxygen. That's this bond right here. That's this one. That's this bond. That one is a polar bond. Polar bonds are strong, so they have a high intensity. But, compared to a double bond, it's not as strong. So the Waves number is going to be lower, right? So that's why you see a very strong signal at a lower wave number because it's just a single bond compared to a double bond. Double bonds are stronger. They have higher wave numbers. So for ethers, you really just look for this signal. You look for the carbon oxygen stretch located at around 1100. 1100 wave numbers. Okay? Any questions about ethers so far? So hopefully by now you're kind of starting to see the patterns, right? We have spectra, they're full of peaks, but we only look at part of the peaks and then we point them out and we move on. So you can kind of expect questions like this on your post-lab quiz. I'm going to give you spectra and I'm going to tell you, hey, here's a structure, partial structure, what functional groups are present. Fill in the remaining functional groups in your structure, right? But you never go in blind. I'm not just going to give you a spectra and be like, tell me the formula. Bro, that's impossible. Literally, you can't do that. Okay. So I'm going to move on to the next drawing. Spectra, sorry. I was going to remove my drawing. There we go. So now we're talking about esters. Well, ester is another compound functional group. An ester is made out of a carbonyl and out of an ether. So it's carbon, double bond oxygen, carbon, single bond oxygen, something else. So an ester is made out of a carbonyl and an ether. That is an ester. So let's look at two different esters, one aromatic, one aliphatic. If it's not aromatic, we use the word aliphatic. So aromatic and not aromatic. So the first one is ethyl butyrate. You see the structure is right here. You can look at that. So let's see. Again, let's start with the highest wave numbers. What's this over here? At 3000, what are those? What are those peaks at 3000? Yep, alkanes, right? And look at your structure, right? There's no double bonds except for the carbonyl. So this is an sp3 CH stretch. That's supposed to say SP. Sorry about that. Yeah, sp3 CH stretch. That's always there. You need to be able to identify it and move on. Be like, okay, cool, it's there. That's not what I'm looking for though. If I have an ester, I'm expecting a carbonyl peak, right? Because there it is right here, carbon double bond oxygen. So let's go to 1700 and let's look for a strong signal. Look, it's right there. This is your carbonyl from an ester. And we're looking for the ether. And based on the previous example, I told you that ethers were found at around 1100. So let's go to 1100. Let's see, 1000, there's 1100 here. Well, there's a signal right there, but remember, it's also a strong signal. So let's look for the strongest signal around 1100. Oh, it's right there. This signal right here for sure is a carbon-oxygen stretching. This one points to this one as well. That is vague. It could be that one. It could be the first one that I pointed to. We just look for the strongest one around that region, and we can safely assign that one. The rest are debatable. So we would have to go to the simulator, do the math. As long as you can point to the strong one, and again, notice how these two look similar, right? They have similar strength, similar intensity. It's just that one is at a lower wave number. So you need to be able to point both of these out, especially if you know from your structure that you have an ester and say, here are my signals. I have my standard sp3ch stretches. I have my carbonyl stretch at 17, looks like it's 1750. And then I have my carbon oxygen single bond stretch at 1200. Let's look at the bottom one. We also have an ester. Here's the formula. But this one has an aromatic ring. And remember, aromatic rings produce sharper peaks. So once again, let's start with the highest wave number. What are these? It tells you right there. These are your CH stretches. They're not as intense as they usually are, but they're still in the same wave number location. There's a carbonyl right here. So let's go to 1700. 16, 17 is right here. Look at that. There is a peak right there at 1700. That is a carbonyl of an ester that is also conjugated. And then look over here, just like in our first example, we have peaks, very sharp peaks, characteristic of our carbon-carbon double bonds between 1400 and 1600. These are just kind of there, like you don't really know that what they are unless you know you have a ring and you're kind of expecting them. And we also have the carbon single bond methyl stretch, right? And again, you look for the strongest signal around 1100. So here's 1000, here's 1100 right here. There's a signal. So that one is definitely a CO stretch. And there's another strong signal over here. So I guess they assigned that one to be the carbon oxygen single bond stretch. And there's two of them, right? There is the carbon oxygen carbon. This is the carbon oxygen from the methyl and the carbon oxygen from the carbonyl. So you get two carbon oxygen stretches there in an ester. You got to find out which ones they are. But as long as you point to the one that is the strongest around that region, you will be okay. So any questions about any of this? The best way to do this is that, so if you just pick the one at 1100, is that wrong? I would give you credit for it because there should be something there. But again, be reasonable, right? If you look at the spectrum, you'll see that the one at around 1300 is the strongest. Well, what's the second strongest around that region? The one at 1100, right? So either the strongest or the second strongest is going to be your carbon oxygen stretch. You can't just pick this one and be like, that's a carbon oxygen stretch. Well, why would you pick that one when there's so many different stronger ones in the nearby regions, right? You could have picked this one, you could have picked this one, you could have picked that one. So it has to be within reason. You're like, well, this is the strongest, this is the second strongest. If you pick any other one, you're just guessing. And at the end of the day, I would have to really confirm with like an accepted example. So again, it's just reason. It's a puzzle. We don't know for sure that any of these peaks are exactly like that one. It could be like you saw how the molecule can vibrate in all sorts of different ways. Like we would have to sit down and do the math to find out exactly which vibration corresponds to that specific wave number. So that's why we don't really pay too much attention to like all of the peaks, only the very characteristic peaks. Any more questions about this? Okay. And notice here that the bottom one that we do have an aromatic ring, but the hills that I told you guys, they're not really there, right? Like these ones kind of look like these ones, and it kind of looks like these ones. So in this case, you can't really use the Oberbands to kind of help you with that. But we were given a structure, so we know that there's an aromatic ring. We don't need much more to guide us. All right. Next slide. Amines. So an amine is an NH or an NH2. The NH bond is the thing that is vibrating. So if you have a primary amine, meaning you only have one nitrogen carbon bond, you have two NH2s. Well, each NH is going to vibrate and it's going to give its own signal. So again, what's this right here at 3000? What are these? What are those peaks right there that I highlighted in the red at 3000? Alkane, right? Yeah, most likely sp3ch stretches, right? Those are always there in every spectra ever. So make sure you know what they are and make sure you know not to confuse them. Well, nitrogen hydrogen is a more polar bond than carbon hydrogen. So it's stronger, so it's going to have a higher wave number, right? So it's going to be in the higher levels, more to the left. But also notice that it's not a very strong signal. It's weak, right? It's at like 60, 65% transmittance. So you're going to look for a weak signal to the left of the stalagmites. And the number of peaks in the signal tells you the number of nitrogen-hydrogen bonds. So for example, here we have hexylamine, we have NH2. Oh, what now? I don't know why if I go too far up on the zoom, it disconnects the thing. So we have NH2. Oh, did it again. Okay, let me just draw it over here so I don't get the computer upset. Gotta clear all the drawings now. Sorry about that, guys. Having some technical difficulties here. Here we go. NH and NH. So those two are these two peaks that you see right here. And then if you only have a single NH, like you see here in piperidine, you only have a single signal. Both of them are weak. Both of them are higher wave number than the stalagmite CH stretches. This is how you know if you have amines. If you have an amine that is connected to 3 carbons, this is carbon, this is carbon, this is carbon. Well, this is now an NC bond. Nitrogen weighs 14, carbon weighs 12. Nitrogen and carbon are next to each other in the periodic table. That's not going to have a high wave number. And it's also a single bond. It's going to be way over in the 1100s, 1200s. So tertiary amines do not show up here. This is only for primary and secondary amines. Any questions about the amines? This is one of the few cases where you can actually get direct structural information from the peaks. It says, are there difference in peaks for isomers? Can you rephrase the question? I'm not sure what you mean by that. Like, are you talking about like strength differences, like wave number differences, like what do you mean by that? Would the spectra look different? Oh, okay. So you're saying like if two molecules have the same formula, but they're different isomers of each other, does the spectra look different? Yes, because the connectivity is different. The way you might have like N2H5, and maybe sometimes one of the nitrogens has two, and the other isomer, there's only one NH. So yeah, you would have different signals. Yes, you know that it's an amine based on the fact that it is a weak peak just to the left of the alkane peaks, and you either see one or two. Yes, yes. And be careful, right? Because this is there a defined range for the amines? I would say between like 3100 and 3400. But this is also the same region as alcohols. So if you have a compound that has an amine and an alcohol, the alcohol signal might just drown out the amine signal. So you don't always see them even though you expect them to be there, right? So it really does depend on what type of molecule you have. You could think of NH like OH, right? NH, we have carbon, nitrogen, and oxygen in the periodic table. Well, NH and OH are very similar in terms of wave numbers and ranges. It's just that OH is bigger because it's more electronegative and it's heavier. So that's why. But I mean, that's why they're both found in similar regions. It's just that don't confuse this with an alcohol. An alcohol would look like this. I'm going to use the color blue. An alcohol would look like this. It would have like a broad signal that's a lot more strong, right? So don't confuse the weak signals of an amine with the broad signal of an alcohol that you expect to see. It's a lot more smooth. Any more questions? All righty. So let's see, moving on. Okay, so now the rest of this time is going to be us just practicing and applying what we've learned. So let's see. This is where you guys have to interact with me and either answer by unmuting or you can type in the chat, whatever's easier. What functional groups are present in here? A carboxyl. I don't know what that means. What's a carboxyl? I think it has another name, right? Exactly. It's a carbonyl. Excellent. Right? Like Lawrence's name is Lawrence, not Laurencio, right? Yeah, yeah. I know you mean carbonyl, but you have to say it. Otherwise, when you say carboxyl, carboxyl is oh man, I thought I had the pen. Hold on. Okay, carboxyl is actually this. This is a carboxyl. So if you say carboxyl, you're talking about this. If you say carbonyl, you're only talking about this. If you say hydroxyl, you're only talking about this. They each have their own unique names. So make sure you're very specific. So yeah, there you guys said that there was a carbonyl peak for sure. Where is it at? Where's the carbonyl peak? 15, 16, 17. You see that? 1700, you have a strong carbonyl peak. And then alkanes at 3000. Yes, you see your stalactites right here. But what else do you see? You're seeing this weird long valley right here, right? What is that? Very broad. Yeah. What is that? It's about 1000 wave numbers broad. So what is that? What is it when something is very broad, 1000 wave numbers, it overlaps the CH3s and it almost looks like a beard, right? Yeah, hydroxyl. Excellent. Yes. This is the OH, the hydroxyl of what? So if you have a carbonyl and a hydroxyl, what is your functional group? Carboxylic acid. That's right. That's right. Yep. So this is a carboxylic acid. So what's this? What's this? What's this? What's this? Bro, it doesn't matter. We have found out we have a carboxylic acid and we don't have any more structural information, so we cannot make predictions as to what they are. Okay? All right, good. Any questions about this example? Okay, next example. What's here? What functional groups are present here? Right? No carbonyl here, right? There's nothing at 1700. So there's no carbonyls. Alcohol question mark? Amine question mark? Okay. Well, if it were an amine, would the signal be strong or weak? And does that look like a weak signal to you? It's at 25%. Exactly. So since it is not a weak signal, it is not an amine. So it must be, Evelyn said it, an alcohol. So this is a hydroxyl, OH. How else can you tell? It's relatively smooth, right? It's not very sharp. It's broad. And notice that in a carboxylic acid, the broth, the breadth, the width, it is 1000 wave numbers. Here, you're starting at like 32 and you're finishing off by 35. So this broadness is a lot less than the broadness of a hydroxyl from a carboxylic acid. But this is still an OH signal. What's all this? What's all these peaks at around 3000? Alkanes, right? These are just CH stretches. That's always present. All of this, we don't know what it is. Probably some bending. They're all in the fingerprint region. We don't see anything else. As far as we know, we have at least one alcohol group and nothing else in here. And that's all the information we can get out of it. We cannot get how many carbons. We cannot get the molar mass. We cannot get the molecular formula. All we know is there's at least one alcohol in this molecule. That makes sense? We okay with that? Okay. Next problem. See, I think I cleared the drawings. And then the next one. Okay. Which ones are here? What functional groups are present here? Amine. That's right. Are you guessing or are you saying it for sure this time? If it is an amine, what is your evidence? What is your reasoning? What is your reasoning? Two weak peaks, right? And they're roughly in the same region as an alcohol, so that tells me it's a strong polar bond. And the peaks are weak, and they're to the left of the stalagmites. So that's roughly where you would expect an amine. There's two of them, so that must mean that there are two NH bonds. So that is a primary amine. This is an NH right here. Um, I always think I have the pencil ready, and then I don't. Reminds me of the COVID days. So this is NH2 right there. And each one of these NHs is one of these signals right there. Okay, what's this? What's this at 3000? Alkanes, right? This is just a CH stretch from whatever else. These are probably CH bends, but we don't know for sure. We don't have any more information. So the only thing we can say for sure is that we have a primary amine and nothing else. Make sense? So when you guys saw the spectra for the first time, you were like, oh God, all these signals and squiggly lines. We only need one or two, three maybe, and that's it. Okay. Next problem. Let's see. What about this one? What is here? Amine NH. So why is it an amine? One weak peak, right? Roughly between 3200 and 3500, right? A very weak peak to the left of the stalagmites. That's usually where we expect to find amines. And so, yep, you see it right there. This is simply just NH by itself. So let's see, where's here we go. This is just NH with two carbons around it. So secondary amine, one NH. What are these right here at 3000? 3000, 2900, 2800. What are these? Alkanes, right? These are your CH stretches, always there, no matter what. There is one more peak that we can identify for sure, and that's this peak right here. It's at around 1100, right? Well, at 1100, we usually find our carbon-oxygen single bonds, right? In this case, we know we have a carbon-nitrogen single bond because it's a secondary amine. And again, nitrogen and oxygen are next to each other on the periodic table. So a carbon-nitrogen single bond should have a similar range as a carbon-oxygen single bond. So I'm going to make the claim very confidently that this peak right here at around 1100 is your carbon-nitrogen single bond stretch. And I can make that claim because I know that I have a secondary amine, which has two carbon-nitrogen bonds. And I mean, if you have one, you must have the other, right? It's very strong signal, kind of looks like a carbonyl, but it is at a significantly lower wave number. Any questions about this? No, 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 not at all. If you didn't include the CN, you would not lose points, but you should think about every possibility that you can identify, right? If this was an ester, you would have to tell me the CO bond. So, I mean, as long as you can identify the amine peaks, that's good enough. But I mean, it doesn't hurt either to identify that CN. Okay. Any more questions about this one?
I have a question,
Yes.
Eduardo.
Yes, go ahead.
It's only identified as a CN because of the amine.
Yes,
If
because
it something else it would be the CO.
if it's something else, it would be the CO. Is that what you mean?
Yeah, because initially we thought it was CO, but then we decided that it was CN because of the amine.
Right. Well, we didn't think it was a CO, right? We are not given a structure, so we don't know potentially if there is a CO here or not. But because we know that this signal is an N with at least one H and this could be carbon, and this could be carbon. Well, we know that if we have an N with one H and two carbons, that we also have a CN bond. And I was trying to make the analogy that you have in the periodic table, carbon, nitrogen, oxygen, and fluorine. Well, you know, carbon, nitrogen, and carbon, oxygen are pretty similar wave numbers. Carbon, oxygen is going to be higher just because it's a more polar bond. And we know that carbon oxygens can be found around 1100. And we know we have carbon nitrogen bonds somewhere. So we can look at this peak, which is the strongest of them all, and very confidently claim that this is a carbon nitrogen peak on that basis. We're using the
Okay.
analogy to a CO bond.
Okay, so you mentioned that the peak at 1100 corresponds to CO.
CN. What I was saying was that we know that COs are usually found around 1100, right? So a
Right.
CO and a CN are similar to each other because they're right next to each other on the periodic table.
Okay.
So if we know that we have a CN from a from a secondary amine, we should look in the same region to see if we find something that is strong that we can use to claim, oh, that's very likely a CN peak right there. And we did find a signal, this one right here. So this is very likely that CN stretch right there.
Okay. I understand. Thank you.
Yeah. Yeah, we're just comparing it. We're using analogies, right? So here's another example. We know carbonyls are at 1700. Well, what if I asked you to give me the predicted wave number for a carbon double bond nitrogen? Well, again, look at the periodic table. Oxygen and nitrogen are basically right next to each other. But this is a slightly weaker bond, so maybe this is going to be at like 1600. We can make predictions like that based on the patterns we learned from Chem 1A and Chem 1B. Make sense? All right, these are good questions. I'm glad you're asking. Thank you. Okay, let's look at the next example. What's here? This one should be a lot easier now, right? You've seen this before now. Alcohol. That's right. This is flat out an alcohol. Why? Because the range is not very broad, the signal is strong, and it is smooth. So this is definitely an OH signal. What are these? We should know by now right away. What are these right here? They're around 3000. They're everywhere. CH stretches. That's right. Everything else, we can't really make a claim, right? You can kind of say this one right here might be like a carbon oxygen where your alcohol is connected, but we don't know, right? We don't know if that's the case. So, I mean, if you make this claim, you have a good chance that it's true, but all we know for sure is that the OH is there. I mean, the oxygen has to be bonded to something, right? But what if it's bonded to a nitrogen? Then we don't know. That could be an NO bond. I don't know. So all we can claim for sure is there's an OH bond in here. All right. Next problem. Ooh, look at this one. A lot of sharp peaks, not very many signals. What is this most likely? Alkene. That's right. Evelyn guessed alkene. Why did you guess alkene? Why not just regular old alkane? The sharp part on the left, right? Well, you can give me the actual wave number. You can be very specific. Give me an actual number. What are you talking about? There's a lot of sharp parts on the left. Which one? 3100. Okay, so let me go to 3100. Yep, there's this peak right here at 3100. This is an sp2ch stretch. That is there if you have an alkene. Yeah, the less than 50%. We have a single word to describe that. What is that word? If it's less than 50%, what do we call that? Wa, we, weak. That's right. It's weak. And then we have a very distinct sharp peak where our usual CHs are at. Remember, there's a type of compound that makes all the peaks sharper. What are they? What makes the peaks sharper? Nope, no carboxyl. Do you see anything at 1700? Remember, I know people like to like yell out carbonyl, carbonyl, but like before you even think that, look at 1700. If there's nothing there, you can't even think that. The amount of bond, well, I mean, you can think of it like the hybridization, right? But this specifically comes from the aromatic ring. Remember, aromatic compounds make everything sharper. And there is a very distinct peak where you normally find your CHs that will show you, yeah, this is a carbon hydrogen aromatic bond right there. And also look over here, we have a few overbands, right? We have like the little hills that we usually see in aromatic rings. If you look here, we have a carbon-carbon double bond signal right there. That is also part of the benzene or aromatic ring. So this is some sort of aromatic compound, aromatic alkene. That's all we can learn from it, nothing else. There is no alcohols, there's no amines, there's no carbonyls. This is just a hydrocarbon that has some sort of ring somewhere. Does that make sense? Okay, how are we doing on time? Alrighty, we got about 10 minutes, so we do have a few more examples to work through, but I don't believe we'll have enough time to get through. You guys asked really good questions, so that's great. You guys have been my most interactive group so far, so I really, really appreciate that. You can look at the slides and see the other examples as well. We can work through them as well. You can ask me during office hours. So let's just power through this one real quick. Um, what's present right away? Like less than 5 seconds, you should see it. Well, there's an alkane that's always there, right? But there's a very characteristic peak, the one that you should definitely know, the Bugs Bunny of the peaks, the SpongeBob of all of them. That's right. This time it is a carbonyl. Why? Because you went straight to 1700 and you saw a strong peak. Now notice it's not all the way to the bottom, but it is at 1700 and it's strong. 1700 and strong very likely means carbonyl. And if you look at your CHs, you'll notice that there's one peak that's particularly lower wave number than the rest. And if you remember from earlier, I told you that that peak usually corresponds to a specific type of carbonyl. This is an aldehyde carbonyl because of this peak right here at around 2900. Not always the case, but in this case it's distinctive, so I can make the claim that that is a CH of a lower wave number that is caused by the aldehyde carbonyl. All right. So let's see. We have about a few more examples, but I'm gonna have to unfortunately skip them for the sake of time. We know that's a NH2 right there. You see that? We know this one is an alkane just because there's nothing else here. So that's just boring old alkane. This is an NH2. Nothing else can be determined. This would be a carboxylic acid because you have that really broad signal, kind of looks like a distorted beard. You have a peak at 1700, not exactly the way it normally looks, but it's at 1700. It's very strong. And you have an OH carboxylic acid signal. So this whole thing is a carboxylic acid. But like I said, this is more practice stuff. I only have a few more minutes, so I do want to leave you with this. On the exam and on the quiz, you're going to get something that looks like this. It's going to have the types of the bonds, the wave numbers, and it's going to have the intensity. In other words, the y-axis. This is why we practice talking about them in terms of weak and strong, etc., etc. The post-lab quiz is going to be in 2 weeks. And the worksheet from the course packet for Lab 4 is also going to be due in 2 weeks. So you have some time. You can go back through the module playlist and look at everything. And now you should be more familiar with the concepts. So maybe a few more things will click. So the last thing I want to leave you with is this. If we go back to the website, there is a website where you guys can please go and practice. So let me go ahead and resubmit. It's called the Spectral Database for Organic Compounds. Spectral database for organic compounds. You can go ahead and click I agree, and you'll see that you should get this signal here. Hold on. Introduction. Nope, that's not it. The zoom bar always blocks out like my my ability to view it. There we go. Okay, here we go. This is what you should see. If you type in the name of a compound, you can see the IR spectra from an actual experiment from that compound. So for example, I'm going to type in acetone and I'm going to click search. I'm going to see right here the first result. It says acetone, IR. You see how it says Y? Yes. You click on it. And there it is. This is your IR spectra of acetone right there. It gives you a structure. It gives you the wave number of the peaks and their intensity in the bottom left box. So again, look up your favorite molecules and then practice doing IR on them. So right here in acetone, you see we have a carbonyl right there. So I'm going to go to 1700. There's 15, 16, 1700. Look at that peak. And if you want the specific number, you can look at the box. So right there, 1750 with only 4% transmittance. So the peak at 1715 wave numbers is going to be my carbonyl peak from acetone. And then look at these two peaks, right? I have a peak here and I have a peak here, very strong, but they have lower wave numbers. And look, I know from my structure right over here that I should have, carbon, 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 hydrogen. Actually, it's not quite what we predict. You might get this question on your post-lab quiz. There's a lot of interesting things happening here. But we can for sure identify the carbonyl. Anything else is kind of uncertain. We do have the CH3s right here. This is your CH3CH stretch. This, mystery. That is a mystery right there. So yeah, read up on some acetone properties. That might help you with a post-lab quiz for sure. Acetone specifically, yes, I would recommend you read up about acetone and its properties on Wikipedia or somewhere. You might get asked a question about the spectra and about acetone in your post-lab quiz for sure. So let's see. Let's look up another molecule. Let me clear the drawings and let's look up another one. Let's do, I don't know, let's do acetaminophen. Acetaminophenol. All right, so there's the IUPAC name. They do have an IR spectrum, so let's check it out. And there it is. So again, you're given your structure, you're given your spectrum. Look up your favorite molecules, look up the medicines, and practice. So right here, look, we have a carbonyl of an amide. So the first thing we do is we look to 1700, 15, 16, 17. It's a little bit lower, but it's right there. Very strong peak. This is your carbonyl of your amide. And if you look at the table, it's at around 16 something, right? So look over here, 1667, and you see that the intensity is 4. So this is at 1667 wave numbers. You see that? And then you have this OH group that is attached directly to a aromatic ring. And remember, aromatic rings make everything sharper. So this time you go over here to this signal, and even though it's not the same usual shape as an alcohol, it's still in the same region, and your structure is telling you that it's there. And you know you have an aromatic ring. Aromatic rings make all the signals sharper. So it just happens that this really broad signal got really, really sharpened by that aromatic ring. But this peak is still an OH peak. This is why it's important to do practice with this website. Because when you see real world examples, when you see the functional groups in different combinations in real molecules, you start seeing that the signals are still in the same wave number, even though they don't always look like the examples we showed you. The examples we showed you are for practice. They're designed to be easy to understand, easy to process. But please go on this website. I will post it on the announcement, the spectral database for organic compounds. I am going to pull some spectra from here for your post-lab quiz. You may be asked to complete a structure. You may be asked to assign peaks. You might be asked to report the numbers exactly based on the table, things like that. But I will be using spectra from here. Look up maybe acetone, water, look up acetaminophen, ibuprofen, aspirin. Look up, you just can't look up drugs. I tried. You can't find methamphetamine. You can't find all these things. This database does not contain that spectra. Okay. But just play around with it. Check it out. Very useful. Play with CHEM223A. Come to office hours. You have 2 whole weeks to let this settle in your brain and think about it. So, take your time. This is going to be our only lecture about IR, but from now on, there's going to be IR problems in the lab worksheets. and they're also going to show up on your final exam. So please make sure you continue to practice IR regularly. Ask me if you have any more questions. Other than that, for next week, all we're doing, well, not all we're doing. Next week, we're starting Lab 5. We're meeting in person from now on until the end of the semester. Make sure you show up on time. Make sure that you're ready with pre-lab procedures. We do have a pre-lab quiz again, and we'll be doing Lab 5. So this concludes our IR lecture. Thank you very much for your attention. Really, really appreciate you being here on a Friday morning from the comfort of your home. If you have any more questions, feel free to stick around and ask me. Otherwise, you are free to go. And I hope you have a very good weekend, and I will see you next Friday.
Um, I got a question.
Yes, sir.
So, as you record the Zoom and like some of the stuff you showed, like the wavelength
Mhm.
ranges, we could take notes for our like our notebooks, right?
Yeah,
Like
of course. Yeah, you can study however way you see fit, whatever helps you study.
including like the textbooks, right?
If you have textbooks that talk about IR, yes, I would recommend that you read them.
All right. Thanks.
Yeah, no worries. Alrighty. Well, thank you guys. I'm going to stop recording now, and I hope you guys have a good weekend.